Number theory gives us prime numbers, isolated, discrete points. Quantum physics relies on smooth, continuous geometry. Bridging these two distinct mathematical environments requires a specialized framework. This illustrates the three-tiered architectural pipeline designed to bridge them. Raw quantum data is filtered at the micro level by spectral projection. In the center, J-theory maps continuous global spaces into stable structures. At the macro level, Logos field theory generates the global field equations. Here we see the master equation of this framework. It uses a contour integral across the complex plane to equate the global geometric J functional directly to the logarithmic derivative of the Adelic L function. This table breaks down the cross-domain mapping. Continuous variables in the geometric domain map exactly to the arithmetic domain's prime ideals. Furthermore, Logos field operator eigenvalues lock to L function spectrum zeros, placing absolute reciprocal constraints on each other. This mapping works smoothly for unramified primes, but the system encounters severe mathematical friction when a prime ramifies. This comparison shows opposing reactions triggered by a ramified prime. On the left, the inertia group acts non-trivially, forcing arithmetic degrees of freedom to shrink. On the right, the geometric side evaluates deeper congruent subgroups, introducing an Artinian defect that inflates orbital volume. This matrix shows how ramification type alters the structure. Tame ramification collapses at the baseline, creating a volume bounded linearly, like a uniform stepped cylinder. Wild ramification cascades through higher Swan filtrations, scaling exponentially to create a massive, highly localized resonance peak. Here is the explicit local upper bound equation governing these distortions. The gap between the geometric functional and the arithmetic L function derivative is strictly limited by the volume of the local minimal K-type packing and the valuation depth. The expanding geometric volume generated by a wild prime exactly matches the sudden truncation of the local L function. The local math boxes itself in. A local prime remains bounded, but the global field contains an infinite number of places. We have to account for millions of isolated wild spikes across the Adel ring and ensure they do not aggregate into systemic divergence. We establish control using the Adelic convergence criterion. By substituting our local bounds into the global variation, we derive a strict global error propagation limit. To prevent the error bound from diverging, three structural criteria must be met: conductor finiteness, spectral gap enforcement, and reciprocity consistency. This diagram illustrates global reciprocity in action. When local geometric defects are integrated through the global trace formula, their phase shifts and local densities interfere destructively. The wild ramification peaks cancel out, ironing the total variation down to zero. With all the ramified defects mathematically neutralized, we can compute the continuous baseline volume for the rest of the unramified universe, starting with the zeta-2 convergence factor. This calculation maps the continuous geometric volume integral of the test function directly to the discrete arithmetic sum using Parseval's identity. The baseline geometric mass evaluates to exactly pi squared over 6, giving the unramified universe a fixed finite volume of roughly 1.6449. Pause the video here, take a higher order periodic test function, x squared, and apply Parseval's identity yourself to find the exact algebraic value for the zeta-4 configuration. Here's the higher order execution. Evaluating the continuous integral for x to the fourth and equating it to the squared Fourier coefficients resolves to pi to the fourth over 90. Notice the sharp drop to 1.08. Deeper configurations resist long-range divergence, dampening unramified background noise entirely. This is the assembled stability state. The unramified baseline forces quantum fluctuations inward via three mechanics. 1. The baseline provides finite spatial topology. 2. L function restrictions act as governing laws. 3. Wild local quantum fluctuations perfectly cancel out through global reciprocity. Through the rigid equivalence of spectral projections, the macroscopic field equations maintain absolute topological stability, operating as a completely self-regulating, globally invariant matrix.